All right, well, good afternoon. And welcome back. I'm really happy to see everybody here today. I was looking forward to getting back. I hope that you were on some level as well. I know that more time, no? Seeing everybody just look at each other like the guy at the front of the room is a little bit loony. For me, it's nice to get back. I like working with you. So we're about halfway through the course. We're going to be starting Unit 5 today, which is a whole cornucopia of stuff. It's a whole mishmash of stuff. We're going to be dealing with absolute value functions and absolute value equations. We're going to be dealing with reciprocal functions and reciprocal expressions. We're going to be dealing with radical functions and radical equations and radical expressions. It's all over the place. And, well, let's get started. The first section of this unit, it's like three separate things: radicals, and then we also deal with absolute value, and we also deal with reciprocals. So this lesson on working with radicals is from section 5.1 of your textbook, and we extended into 2 days. This is an extension of what you learned in Math 10. So this shouldn't be that bad in terms of difficulty, okay? We're going to be converting from mixed to entire radicals, and just by a show of hands, how many of you remember what a mixed radical is as opposed to what an entire radical is? Okay. So something like 2 root 3 is a mixed radical, whereas something like root 12 is an entire radical. And it turns out that 2 root 3 and root 12 are exactly equal to each other. Okay. That's from Math 10. We're going to extend that to higher, what we call indices or indexes of roots. We're going to be looking at cube roots and fourth roots and fifth roots and sixth roots and eighth roots and hundredth roots if we want to. The principle is going to be the same. So we're going to be converting from mixed to entire and entire to mixed radicals, and we're going to be adding and subtracting radical expressions, which is a little bit of what you did last year, but not a lot. So to begin with, convert all of the following entire radicals to mixed radicals. And I know that this should be easy. This should be very easy because we've been doing it already this year. But I want you to pay careful attention to my explanations, because as soon as we get to cube roots, it's going to be more complicated. How I teach this, if I were teaching a Math 10 class, I would say that what you were looking for are 2 factors of 44. By the way, the number 44 is called the radicand. The whole thing is called a radical. The number under the radical sign is a radicand. I would say, give me 2 numbers that are factors that multiply together to give 44, where one of those numbers is a perfect square. And it's staring us right in the face. It's 4. 4 times 11. So in Math 10, this is how I would teach it. And I always put the perfect square factor first. In Math 10, you are taught the following. You were taught that the square root of a product is the same as the product of the square roots. So what I'm saying is, to show an additional step that I don't believe we need to show, is that since 44 is 4 times 11, the square root of 44 is the square root of 4 times 11, I am allowed to write root 4, root 11. And you can verify that with your calculator, but that's Math 10. And by the way, most of the work we do here is not done on the calculator. Okay? We do not want to enter root 44 on our calculator and write down the answer. Okay? And then what you do is you say that the square root of 4 is 2, so this is 2 root 11. And I hope on some level that you're bored by that question, because it's really simple. As I said in the previous unit, we've been doing that, haven't we? When you get the square root of b squared minus 4ac, you're expected to simplify that. But I'm going to show you a different way to do this. And it could very well be that your Math 10 teacher used this method or not. But many of you will need to use this method today. Not for this question, but for more complicated ones. The idea is you want to take 44, and I prefer just to look at the number 44, not the square root. You want to take 44 and perform what's called a prime factorization of 44. What that means is we want to write 44 as a product of primes. Prime numbers are numbers that have no factors other than 1 in themselves. So prime numbers are, I can't remember if 1 is considered prime. I think for some reason, for some technical reason it's not, but it doesn't matter. 2, 3, 4 is not prime, 5, 7, 8, 9, 10, 11 is prime. These numbers are all only divisible by 1 in themselves. 9 is not, because it can be written as 3 times 3. So, and I'm sure this will ring a bell, this kind of deal. And you might go 4 and 11, and whether you decide to put a multiplication sign in there or not is up to you. This is not the work you would need to show, okay? And then you would say, well, 4 is 2 times 2, so now we're at 2 times 2, and this 11 just comes down times 11. So going back to the original question, and I know this is boring for some of you, but as soon as I get to cube roots and fourth roots and fifth roots, you need to know this. Many of you are sitting there going, why can't I just do this? You can. But can you do it with a fourth root or a fifth root? I don't know. It gets complicated. So now we go back to the beginning and we say this problem now can be rewritten as root of 2 times 11. And you're going to use, this is obvious I think for many of you, but you're going to use a property of radicals, these are radicals we're dealing with, that says that the square root of x squared is simply x. Let's try something. Let's try it. Take your calculator and pick a number with a decimal. 2.5, 3.78, whatever. You pick your own personal number and square it. Now take the square root of that number squared. I like that some of you aren't even bothering to do this because you know what's going to happen, right? You're going to be back to that number. That's like me telling you to double something and then cut the result in half. So this means, everybody, that the square root of x squared is simply x. And I'm going to extend this idea into a different visual for you and say that anytime you have two identical factors under a square root, you can move them outside of the square root and write it as one of those factors. And the reason why it's two of them is because this is a square root. So these two 2's here, we have a pair of 2's. Inside, we can simply write it as a single 2 outside. And I know this, that everybody in the room would much rather, well, most of you would much rather just do the 4 times 11 and the square root of 4 is 2. I know that, okay? Anyway, food for thought. There's another way to look at it. Regardless, any questions with this first example? Okay. Root 48. Well, let's try it the second way first. And how many of you use that second method regularly? Probably, how many of you were taught it and then you ended up moving away from it? Okay. Well, we're going to probably move back towards it now. So if I were doing this, I would be looking for two numbers, one of which is a perfect square. How many of you have the two numbers right away without using your calculator? Okay, hang on to them. Let's do it the other way. Let's take 48 and let's break it up. Now here's a tip for you. I know that 48 is even, and I know that many of you will want to say 2 and 24, and you'll keep having all these 2's that pile up. Why don't you do this instead? I mean, if you know your multiplication table, you know 48 is 6 times 8. And really, everybody should know 6 is 2 times 3. And with a little bit of thought, just a little bit, 8 is 2 times 2 times 2. I don't think we need to write 8 as 2 times 4 and then change the 4 to 2 times 2. This is 2 times 3 times 2 times 2 times 2. And you can verify if you like right now, either in your calculator or with your brain, that 2 times 3 times 2 times 2 times 2 is 48. Okay, what this means is this kind of method that you were probably originally taught, that you moved away from, that now I'm steering you back towards, says root 48 is 2 times 3 times 2 times 2 times 2. And it's a square root, which means we can extract things that appear as pairs. So do I have a pair of identical items under the square root sign? Well, yes. I've got two 2's right here. So I can get rid of them and write a single 2 outside. Do I have any other pairs? Well, yeah, I have this 2 and this 2, which are another pair of 2's. Another pair of identical items. So what's going to happen is the green 2's come out and we write them as a single 2 because the square root of 2 times 2 is just 2. Did I just say the green come out? Doesn't matter. The green comes out because there's 2 greens. 2 times 2 is 4, square root of 4 is 2. And the blues, 2 times 2 is another 4, the square root of that is 2. Or you just say, I've got 2 of them, let's put 1 out on the outside. And we're left with 4 root 3. And on some level, I like the simplicity of this. All the hard work is done here. When you do it the other way, you have to rack your brain for numbers that multiply to give a perfect square. Now, how many of you know what the 2 numbers are? So fewer people. It's 16 and 3. Have you ever simplified one of these? Let me write it down. Have you ever simplified one of these, but then it turns out you can simplify it further? That's happened to all of us. That's because you didn't find the biggest perfect square. You'll never have that problem if you use the method on the right. Root 16, by the way, is 4. So it's 4 root 3, which is what we have peeking out of the bottom of the screen. Right, this is what we had. If I can grab it. Oh, I can't. All right, that's what we had. So any questions with B? All right. Cube root of 400. So if you were going to do this the way that you all want to do square roots, here's your problem. What 2 numbers multiply to give 400 where one of them is a perfect cube? Okay, do you see the difficulty here? You get so used to knowing what the perfect squares are, now you got to try to remember perfect cubes. Now I know what they are because I've worked with numbers more than you. So let's not do it that way. Let's take 400 and tear it down. Tear it apart. I know 400 is 4 times 100. I know 400 is 4 times 100. I'm going to cut a couple of corners here. 4 times 100. Well, 4 is 2 times 2. Well, I'm going to really take a lot of shortcuts. 4 times 100. There's the 4. 100 is 10 times 10. But 10 is 2 times 5. And you know what? To be honest, I don't care how you get to this point. I care that you get to this point. This would never be a written response question. I don't want to see how you got the answer. But you should verify, and you can do this now on your calculator, that 2 times 2 times 2 times 5 times 2 times 5 gives you 400. So what we have then is the cube root of 2 times 2 times 2 times 5 times 2 times 5 times 2. The order that I wrote these in, the 5s and the 2s, I flipped them for some reason when I wrote them in, but they're all the same numbers. Now, I would say to you that this stuff in the top right corner of the screen is simply scrap paper work. Okay, it really is. Let me ask you a question here. Can you use your calculator and figure out for me what this has nothing to do with this question directly, what the cube root of 1,000 is, or use your brain to figure out what the cube root of 1,000 is? Your cube root function on your calculator is in the math menu. So you would go math and you'd scroll down to cube root. It looks like a mess. That's never how we would write it. Of 1,000. And what do you get? 10. And how many of you knew it was 10 by looking at the number 1,000? Can somebody explain why the cube root of 1,000 is 10? And not because the calculator said so. Yep. Yep.
There's 3 zeros in 1,000.
Right, there's 3 zeros in 1,000. In other words, 1,000 is, look at my fingers, 10 times 10 times 10. 10 cubed gives you 1,000, which means the cube root of 1,000 is 10. 5 squared is 25, so the square root of 25 is 5. And I just finished explaining in A and B that when you have a pair of identical factors under a square root, you can get them out of there by writing a single factor outside. Well, that means that you could do the same kind of thing here and say this is the cube root of 10 times 10 times 10. There's 3 10s under a cube root, so I can remove the 3 inside and write 1 outside. And what I'm getting at now is that when I look at what we have here, I have 3 2s right there. And the cube root of 2 times 2 times 2 is 2. So I don't need to write 3 2s there. I can write 2 cube root. And I have these leftovers. Do I have any more triplets in there I can suck out? No. Yeah.
You have an extra 2 on the left-hand side. That equals 800.
Do I have one too many 2s in what I wrote? Thank you. Thank you, Keegan. Oh, I see what I did. I went 5 2, 5 2 at the end. So do I have any more triplets that I can pull out? Well, no, I have a 5 and a 2 and a 5. So those leftovers, you're not going to write 5 times 2 times 5. You're going to write, I think it's 50, isn't it? Yes? Okay, now, going back to the old method, I'm just curious. I mean, I know this is the case. How many of you knew the 2 numbers that multiply to give 400 were 1 as a perfect cube? So you don't know your perfect cubes yet. You will by the time you hit Math 30. It's 8. 8's a perfect cube. And 8 goes into 400 50 times. 8 times 50 is 400. And the cube root of 8 is 2, so 2 root 50. 2 cube root 50. But imagine it was the 5th root, and I'm going to say, okay, what's a perfect degree 5 number that divides in? I don't think too many people will get that. Let's try one more. Number 2, convert all of the following mixed to entire radicals. So now that I've established if it's a square root and you have 2 identical numbers under the square root, they become 1 inside, or outside rather, then we can say if you have a number outside, when we put it in, we have to put 2 of them in. So there's a 5 that's outside of the radical sign. When I put it in, it becomes that. And I'm going to write it a different way. Do you agree, think about this carefully, that the square root of 5 squared is 5? So I don't have to write 5 times 5 under there, I can put 5 squared. And that's going to become useful when the exponents are something like 11. We don't want to write 5 times 5 times 5 11 times. So now we multiply these out. I want to say 325. Thank you. And we're done. So, square roots, if you have 2 items inside, they become 1 outside. If you have 1 item outside, they become 2 inside. Okay, well, this is going to be the square root of 3 squared times 2. Why 3 squared? Because it's a square root. So this becomes root, I believe that's 18. Pretty basic stuff so far. 4 cube root 6, well, I'm going to put 4 cubed inside because, and you need to listen and think of the words, think of what I'm saying. The cube root of 4 cubed is 4. We want just 4 without the cube root on the outside, so we have to take the cube root of 4 cubed on the inside. And now we figure out what that is. $384. Cube root of 384. Express each, oh, well, this is certainly different. There's letters, okay? Algebra. For each entire radical, write it as a mixed radical in simplest form. Identify any restrictions on the variables. So I want to leave the restrictions until we get done A, B, and C and all the parts, okay? We'll talk about the restrictions in a bit. So I hope you understand that this method here of just breaking things into a perfect square and the rest is kind of a dead end here, isn't it? Let's break it apart. And you're going to find your own ways to get shortcuts here. I want to break this apart, and I'm going to choose to do it all under the square root sign, or cube root sign. So, what's 120? I'll do this 120 off on the side. That's 30 times 4. You could have chosen 60 times 2. You could have chosen 3 times 40. 10 times 12. 4 is the 2 times the 2. The 30 is 3 times 10, but 10 is 2 times 5. Make sure I get the right number of numbers this time. You can confirm for me that 3 times 2 times 5 times 2 times 2 is in fact 120. So we can put these guys under here. We have a 3, a 2, a 5. I'll be more careful this time. And then 2 more 2s. And then we have the f's. Okay. Prime factorization means f to the 5 is f times f times f times f times f. 5 f's as factors. Since this is a cube root, everyone, we are looking for things that occur in triples. So there are 3 2's. But we also have 3 f's. And that means that the 3 blue 2's under the cube root can be written as a single 2 outside. The 3 green f's under the cube root can be written as a single f outside. And the leftovers get packed back together. So I have 3 times 5 is 15 f squared. And again, we're going to save the restrictions for the end. And that's the answer. I'm going to slowly train you to maybe develop your own shortcuts. Since it's a cube root, we would be looking at extracting triples. So how many of you see that instead of doing the f, I think that was 5, you would say f to the 5 is f cubed, f squared, and this would go outside the cube root. For each 3 of those variables, it becomes 1 outside. All I care about, everybody, is you get the answer. I don't care about anything else. Okay. 4th root of 32m to the 7. So if you did this the old school way, you'd be saying, what's a number that divides into 32 that is a perfect power of the exponent 4? And now I happen to know what it is. But that's because I teach Math 30, and we do this all the time with exponents and logarithms. So instead what we do is we prime factorize 32, and I'm going to give you a minute to figure out what 32 is in prime factored form. I think it's 2 to the 5, isn't it? 32 is 4 times 8. 4 is 2 times 2. 8 is 2 times 2 times 2. It's 5 2's. So whether you choose to write 5 2's here, or I'll put an alternate approach in green, or write this, come on, is up to you. I mean, 2 to the 5, there's 5 2's, so that's 2 to the 5. Why am I grouping it as 2 to the 4 and 2 to the 1? Well, because it's the 4th index. I'm taking the 4th root. How many m's do we have? So you could do this. You could go m, 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 m. Get rid of this stuff. It's just scrap paperwork. You can do that, or you can, I don't know if visualize is the right word. We're trying to extract groups of 4, and I have m to the 7. Is there going to be 4 m's in m to the 7? No. So I can put m to the 4. Are there going to be another group of 4 m's? No? Then I write m to whatever is left over. I like this part in green. I think this is cleaner. Because then I can just say that this becomes a 2 outside. This becomes an m outside. I don't know why I've switched to red. And then the rest of it is 2 times the m cubed, and it's a 4th root. See, if you do it this way, I hope that for those of you that do want to do it the way it's in brown, you will graduate towards a more streamlined approach later. Because if you do it in brown, then you're going to have to do this. There's a group of 4. You're going to have to count these off. There's a group of 4. You get the same result. It's just visually a little more hard to wrap your head around. Any questions with B? All right. Back to a square root. There's nothing that says you can't go back to the old way of doing things for a square root. 9 times 7 is 63. But I'm going to write this as a prime factorization. 3 times 3 times 3, whoops, times 7. Don't just sit there and write the stuff down. Make sure you know how I'm getting that's 63. I'm not going to write n times n times n. Well, do you agree, I'm not going to write all that if there were an n squared, I could write that as a single n outside? Okay. Is there an n squared in n to the 7? Yeah. Is there another n squared in there? No. Is there another n squared? Is there a fourth n squared? No. What do we have left over, Taya? Just n to the 1. Okay, so that means anything with a squared is going to go away and become a single base on the outside. Is there a p squared in p to the 4? Yep. Is there another p squared in p to the 4? And that's it for the p's, right? So I'm going to underline in red the stuff that is going to go away. All of this stuff is going to go away from under the square root sign and be replaced outside with just that base. So this 3 squared becomes a 3 on the outside. This n squared becomes an n. This n squared becomes an n. This one becomes an n. This p squared is a p. This one is a p. And what do we have left? We have the 7 and the n. And of course, we wouldn't write 3n, n, n, p, p. That's what we would write. All right. Let's go back. Let's do the restrictions. I have a question for you. And when you do restrictions, this is something you're going to get used to over time. It doesn't matter what this simplifies to. Restrictions tell us what the variables are allowed or not allowed to be in this expression. Now, can somebody tell me why there are no, let me write this down first. There are no restrictions on f. What that means is any real number for f can be put into that expression, and you are allowed to calculate the cube root of 120f to the 5. There are no restrictions here on f, but here m has to be greater than or equal to 0. Let me write both of those down. Well, I'll just freeze one of the monitors. So here's B. I'm telling you there is a restriction. There is a handcuff being placed on what you are allowed to do here. And you are not allowed to put a negative number in for m in that expression. But in this expression, which is on the screen on the left, you are allowed to put in any number, including negatives. Owen, do you know?
It's because you can take the cube root of a negative number and
Right.
not if the root number is even, then you can't have a negative number in there.
Right. So let's just talk about something with numbers. I'm going to use 64. What does the square root of negative 64 mean? It means what number do you square to get negative 64. Well, when you square a number, you're always going to get a positive. Right? And this is why I think your calculator is going to call it a domain error. If I say, well, I want to figure out the square root of negative 64, I kind of get slapped on the hand by my calculator and say, well, there's an error. Oh, non-real answer. I'm trying to take the square root of a negative. But if I were to say to you, what is the cube root? So this is not defined. If I said, what is the cube root of negative 64? It's going to be equal to negative 4. Because negative 4 cubed will give you negative 64. And by the way, and this is something that you really need to pay attention to, when I ask you to figure out what the cube of negative 4 is, if you do this, you are not using your calculator right. Let me ask you a question. I know I'm going to be dancing all over the place here, but do you agree that if I tell you to square this number, you have to get 9? Okay? If I tell you to square that number, you have to get 9. This is not going to give you, this is not going to give you 9. It's going to give you negative 9. This is a discussion you've had in Math 10. What this means is negative 1 times 3 squared. So when you are raising a negative base to an exponent, you need brackets. So if you want to figure out what this is, you go bracket negative 4 end bracket cubed. It's not going to matter in this case because it's going to be negative anyway. So anytime you have an odd, it's called an index. You learned that word in Math 10. Anytime you have an odd index of a radical, there are no restrictions on the variables in these types of questions. I say that because things can change later. Okay? So there's no restrictions there. Are there restrictions here? Yes. If m is negative, this is tricky, and you take that negative value of m and raise it to a 7, you're going to get a negative. And you cannot take the fourth root of a negative. When you look at C, are there restrictions on n? Can n be negative? No, because then you would have a negative number raised to the 7, which will be a negative number, and you're going to take the square root of it. Not allowed that. So n must be greater than or equal to 0. Are there restrictions on p? No, because it's p to the 4. You're raising p to the 4 first, then you're taking the square root. So even if p were negative, when you raise it to the 4, it will become positive because 4 is an even exponent. There's a lot going on here. Any questions with the restrictions? All right. Convert each mixed radical to an entire radical. Well, this should be a piece of cake now, because if we want to move that 4x underneath, we have to square it. And there's nothing wrong with you writing underneath 4x times 4x. 4 squared is 16. Multiplied by 3 is 48. Root x, square root of 48x cubed. Now, what are the values of the variable for which the radical is a real number? Is simply saying, are there restrictions? And we want to look, this is our eyeball, everybody. We want to look at the original expression. We don't care about what it becomes. Not that it matters in this case. There's an x under there, which means x must be greater than or equal to 0. I didn't really address this, but if x is 0, that's allowed because you can take the square root of 0. J cube root, j to the 4 rather, cube root j. I'm not sure why I decided to have brackets there. Let me rewrite it. It's j to the 4 cube root j. How many of you just, I don't know, I'm just curious. How many of you see it's j to the 13 underneath the square root? Because what we have to do is when we move that j to the 4 underneath, we have to include 3 of them. If you move something from outside of a cube root to inside, you have to cube it. And that means j to the 4 times j to the 4 times j to the 4, and then times j, which is the cube root of j to the 13. I mean, I'm going under an assumption here that you understand when you multiply common bases, you add the exponents. Very basic exponential rule from grade 9 and 10. No restrictions because it's a cube root. So who cares about negatives? They'll all work their way out. 2k squared, 4th root, 4k. I guess first of all, k must be greater than or equal to 0. Because it's an even root. You can't take an even root of an odd number. Sorry, you can't take an even root of a negative number. So we can move all this stuff outside, inside, but we have to raise it to the 4. Whether you want to write underneath there 2k squared times 2k squared times 2k squared times 2k squared, or 2k squared to the 4, I don't care. One way or another, we also have to include this 4k. One way or another, we do have to take 2 to the 4 and understand that's 16, which you would get if you wrote 2 times 2 times 2 times 2. And from Math 10, you need to understand when you have what we call a power of a power, you multiply the exponents. So k squared raised to the 4 is k to the 8. And then we have another 4k. Again, I don't really care how you get here. This is not written response. This is finding out equivalent expressions. And now we can go 16 times 4 and k to the 8 times k to the 1. And I get the 4th root of 64 k to the 9. Any questions with that one? All right. Who can tell me what 7 root 5 plus 3 root 5 is equal to? It's a Math 10 question, I believe. Maybe not. Doesn't matter. Taya? Can you say that again?
8 root 5?
Where are you getting the 8 from?
Sorry, 10. Oh my
Thank you.
gosh,
Yeah,
10.
no, that's okay. Hey, you see me do that all the time. I knew you knew. 10 root 5. See, when you see 7 root 5, which is how we say it, it means 7 times root 5. And it means I mean, you would never solve the problem this way, but this is 7 root 5. That's what it means. And then we have the 3 root 5, so we're going to add 3 more. You get 10 root 5. This is why 7x plus 3x is 10x. It's like 7 kittens plus 3 kittens being 10 kittens. The coefficient is how many of those things there are. So this is simply 10 root 5. I think I already used the word. Do you remember what these terms are called? They're like terms or similar terms. Okay. Are these similar terms? Yeah, they are root 14s. So, let me bring that other monitor back. They are root 14, so we have 18 of them minus 17 of them. I have 18 pizzas and I eat 17 of them, but not by myself. What do I have left? I have one pizza. So here we would have 1 root 14 or root 14. Still with me? Okay. Are these like terms? No. So we can't add them. This is like me saying to you, simplify 4x plus 5y. It's like saying you have $4 plus 5 cherry danishes. What do you have? You have $4 and 5 cherry danishes. You don't have nine monstrosities that are a mixture between dollars and danishes. It doesn't work that way. Are these like terms? No. So can we add them? Well, I'll tell you what, we can. Because root 18 can be simplified. Root 18, and I want to pause here. You know that business with the factorization and all that? Can we agree that when it's something like root 18, we don't need to do that? We can say, what are the numbers that multiply to give 18? They are 9 and 2. Can we simplify root 8? Yeah, because it's root 4, root 2. How many of you are capable of seeing right now these two terms are about to become like terms? They're going to become root 2's. Be very careful here. This is going to become 12. 4 times the 3 is 12. It's very tempting to write 36, and I see it all the time. This is simply 2 root 2. So we get 12 root 2 minus 2 root 2. Well, that has potential. Because now they're like terms. Let's go to D. No, let's go to F. That was D. Let's go to F. I'm going to skip a couple of these because we're running a little late here. Are these like terms? No. Root 4c cubed are different than root 9c cubed. But can we simplify these? Well, this root 4 can become a 2 on the outside. Can we extract any c's? How many are inside that are going to go away? 2. What will they become on the outside? 1. So this is a number of root c's, or a number of c root c's, depending on how you look at it. We have minus 5. Can this 9 make an exit out of the square root? Sure, it becomes 3. Can we extract any c's? Yeah, we have c cubed, so in there is a c squared, which becomes a single c on the outside, and root c. So I have 2c root c minus 15c root c. And if I were you, and I'm not, so you have to decide, I would not think of this as a number of root c's. I would think of it as a number of c root c's. $2 minus $15 is negative $13. 2x minus 15x is negative 13x. 2 c root c's minus 15 c root c's is negative 13 c root c's. And by the way, I don't know if it's asked about restrictions. No, it didn't. But you could put here for this one, c needs to be greater than or equal to 0. Let's try just one more. Let's skip one again and let's go to h. Are these two terms like terms? No. But if we simplify them, maybe they become like terms. My hope, everybody, is that you see some of these numbers frequently enough that you know what they factor into. That 16 is 4 times 4. And each of those 4s is 2 times 2. The 54 is going to require a little bit more thought, I think. You know, my brain says, and I don't necessarily need to write it down, you might or might not. My brain says 54 is 9 times 6. And 9 is 3 times 3. And 6 is 3 times 2. Even for something, everybody, as simple as this, 16 I don't need to double check. But for something as simple as this, I would want to double check myself. Is 3 times 3 times 3 times 2 54? And it is. But I want you to get in the habit of double checking. So these 3 2's make an exit to become 1 2. And we're left with a single 2 inside. These 3 3's make an exit and become a 3 on the outside, leaving, well, there you go. There's our like terms. They are numbers of cube root 2's, specifically 17, because this is 15 cube root 2's. You know, other than the restrictions and the fact that we're dealing with cube roots and fourth roots, etc., which admittedly is a big deal, this is just applying what you learned in Math 10.